Welcome to this episode of PS 100. Let's rock and roll with some waves. Before we dive in, let's review some basic wave vocabulary with this guitar. Here, the string is our medium. Before I pick it, it's in its equilibrium position, which is at its lowest or resting energy. When I pick the string, energy transfers from my hand through the string, causing it to vibrate as the energy begins to move back and forth. And that's what a wave is, traveling energy. Let's slow the wave down so we can get a better look. When I first pick the string, you can see the wave spreads outward from the pick in both directions. We call this propagation. The wave's amplitude is the distance between the string's equilibrium position and the points of maximum disturbance. These high and low points are called crests and troughs. Measure the distance between two crests and two troughs, and you'll have the wavelength. Count the number of crests that pass my finger every second, and you've got the frequency. And then there's the wave's speed, which measures how fast the wave propagates. We measure the speed of a wave the same way that we'd measure the speed of a car or any other traveling thing, by a unit of length per unit of time. There are many types of waves. For now, we'll just focus on three of them: shear waves, surface waves, and compression waves. Shear waves are transverse waves, which means the molecules in the medium vibrate at right angles to the direction the wave propagates. You'll see this sort of wave in a crash cymbal. Let's watch that in slow motion. As you can see, when I hit the cymbal, it vibrates up and down. But you can also see that the wave spreads, or propagates outward, in a line perpendicular to the direction the cymbal's molecules are vibrating. And there's your right angle. You'll also find shear waves traveling through other pieces of the drum kit, like the snare drum. In extreme slow motion, this drum skin seems to move as fluid as water. This brings us to surface waves, which is what you're seeing when you look at ripples on a pond. You'll also find surface waves on solid surfaces like this drum skin all the time. And to the naked eye, a surface wave looks basically the same as a shear wave. So what's the difference? Surface waves, as the name suggests, can only travel across the surface of a medium. They can't travel through the middle of a liquid or a solid. Now, let's head over to the quietest room on campus, the anechoic chamber, where we're going to check out compression waves with the national parks. Believe it or not, you're surrounded by compression waves every moment of your life. Just listen. What you hear are compression waves. That's what sound waves are. And in contrast to shear waves and surface waves, compression waves push and pull molecules along in the direction of wave propagation, creating waves of compressed molecules. You can see this when we slow down the video of this speaker cone. As it pumps in and out, it pushes and pulls the air in the same direction the sound waves propagate. See where the molecules are clumped closest together? Those are your crests. See where they're most spread apart? Those are your troughs. If we graph the path of one molecule of air on the y-axis over time and represent time on the x-axis, you see the sort of wave pattern you'd expect. So we've already looked at the shear waves and the surface waves from the slow-mo footage. But what about the compression waves? 1, 2, 3, 4. The compression waves are actually created by the shear and surface waves vibrating through each instrument. And the interplay between shear waves, surface waves, and compression waves doesn't stop there. The energy the national parks put into their performance transfers and transforms over and over before their music lights up your brain. That energy will even travel as an electromagnetic wave for a while, but that's a story for another video. That's it for this episode, but you'll find more science and research opportunities for BYU undergrads in the description below.